All right, welcome to topic 9.3. In this topic, we are going to interpret heating and cooling curves. Next week, in the next lesson, we will work on determining quantity or calculations numerically, looking at values related to heat and cooling of a material. So the first thing we're going to do is review our 6 types of phase changes. So in order to do that, we're going to go back even further to one other topic that we covered back in first semester, and that is 2 terms, and that is endothermic and exothermic. And I'm going to pick 2 different colors for each of these. So when we see the prefix endo, that is telling me what's happening to the heat. And again, exo is telling me what's happening to the heat there. So in an endothermic change, heat is being absorbed from the surroundings, as where exothermic is releasing energy. Okay? So that helps us understand what's happening in terms of relative amounts of kinetic energy, motion energy in a solid, liquid, gas. Of the 3, gas has the most kinetic energy, liquid is the intermediate, and solid has the least. So in the arrangement of what's going on in the system, we have to understand, is there more or less energy, meaning was energy absorbed or released? So here, a solid to change to a liquid has more kinetic energy, it has more motion and energy relative to the solid. So that means this was an endothermic change. So I'm going to write in my pink color. And so the phase change is melting, which is also referred to as fusion. If we go one step further and continue to absorb energy, because again, gas has more kinetic energy relative to a liquid, that phase change is vaporization. If you recall from 9.2, there are 2 types of vaporization: evaporation and boiling. There's an even greater absorption of energy going from a solid with minimal kinetic energy to a gas with the most amount of kinetic energy. That would also be considered endothermic, and that was called sublimation. Going in the opposite direction, we're now going to start releasing energy. Things are going to move slower, and the particles therefore get closer together. So when a gas loses as much energy as possible and becomes a solid, the inverse or opposite of sublimation is deposition. As we take a gas and change it to a liquid, again, there's a loss of energy. Particles move closer together. This is called condensation. Here, a liquid losing energy to become the solid state, that is freezing, also sometimes referred to as solidification. Okay? That's going to help us when we look at an actual heating curve and cooling curve. So when we understand energy and phase changes, there's 2 forms of energy we need to account for. So the thing that's interesting as chemists is that ideally and hypothetically, any material, whether it's an element or a compound, can be in all 3 states of matter. It can be a solid, liquid, gas. It's just a matter of what temperature does that happen at. So how in the world do we know what temperature something melts at or what temperature something boils at? It's because when a phase change happens, the temperature is actually staying the same. You would think that if you are melting an ice cube in your hand, that the temperature of the water is going to be increasing. But what actually happens is the temperature is constant, and that means the average motion energy of the water molecules is staying the same. So what is actually happening during a phase change is that heat that's either being added or removed. In the case of melting the ice cube, your hand is adding heat to the system. What it is actually doing is allowing the molecules to move further apart from one another, going from the solid state to the liquid state. We're not making them move faster. What it's doing is breaking up the relative placement of them. And so what we see is temperature is constant during a phase change because of those intermolecular forces. We're going to look at a material in a lab situation and show you and prove to you that phase changes happen at a constant temperature. There are two kinds of energy that we want to describe in phase changes, and that is potential energy and kinetic. We've talked a lot about kinetic. It's motion energy. We measure motion energy through temperature. So when you're describing something at 100 degrees Celsius, you're describing the overall average kinetic energy of the molecules in it. The higher the temperature, the higher the kinetic energy. The lower the temperature, the lower the kinetic energy. As where potential energy is stored energy. And we're going to talk about what happens to potential energy during an actual phase change. So heat is a form of energy, and there are two things that can happen because of heating. And again, heating can go in two different directions. You can add heat, you can remove heat. But what can happen is you can either cause a change in phase or the change in the substance's temperature. You cannot do the both at the same time. Heat is doing one thing to the material or the other. So you again are either changing its phase or you're changing the temperature. They are never happening at the same time. You're either doing one or the other. I'm going to kind of skip over this first bullet point, talk about it more with the graph. But the big thing is when we're defining temperature, it's the scale, like Celsius and Fahrenheit, that measures the speed of the molecules. Again, speed being kinetic energy. We use that to then infer and measure how much energy the molecules then have. So again, heat and temperature are not the same. So what I have here are a heating curve, two graphs, heating curve, cooling curve. So I'm going to continue to color code here and bounce between this and the information that goes with it. So we're going to actually answer this information first before we even look at the questions. So I'm going to pick a color to highlight this segment here. The thing I like about this particular heating curve is that it shows particle diagrams. And during this entire segment from minus 40 degrees to 0 degrees, we have the solid. And let me rewind real quick. With the heating curve, there's an X and Y axis. The X axis really a lot of times doesn't end up being the most important axes in the graph. It can be one of two things. It's either the amount of heat added or it's time. They kind of bounce between preference in that variable. But the Y axis will always be temperature, usually in Celsius, okay? So while I can look as I look at the overall start and end point is I'm starting at minus 40 and heating the substance all the way to 130. And during this first thing, what I see happening is it's at its lowest point, and I can see that I have 5 segments. When you take something through a complete heating curve all the way through your 3 states of matter, meaning 2 phase changes, there breaks in 5 segments. So everything up to 0 in this sloped part is going to be a solid. And when I look at this segment, the temperature, the slope is going up, so temperature is increasing. So if temperature is increasing, that means the particles have to be moving quickly. I mentioned earlier, heat can do one of two things. It can either cause a change in temperature or cause a change in phase. We see a change in temperature. Therefore, this is not making the molecules break up that attractive force between each other. So the potential energy is staying the same, and we are not changing the material's phase yet. However, when we get to a plateau, we know that there's something happening here. Plateaus mean phase change, okay? So think of P and P, plateau, phase change. So what we have here is when you are thinking about melting an ice cube in your hand, it's not really solid, it's not really liquid, it's both, okay? So it's a hybrid between these two states of matter. What we see happen is our slope is 0. Therefore, temperature is not changing. So if the particles are not increasing or decreasing in temperature, kinetic energy cannot be changing because they are, again, temperature is a reflection of kinetic energy. So what's happening here, and this is kind of nice by having the particle diagram, is we're going from something that is tightly packed together in the solid state, and we're breaking it up so they are moving further apart from each other. So what's happening here is we're increasing the distance in which they are packed, not how fast they're moving. So this is where the potential energy is increasing because those particles move further apart. So because this is a solid liquid mix, that phase change then is melting or fusion. Once we get through that segment, onto segment C, we are back to another sloped line. We are out of that hybrid of having a solid and liquid, and we now are fully in the liquid phase. we see that temperature is going up because we have a positive slope here. So that means if they are measuring an increase in temperature, that means we have an increase in kinetic energy. That means that the particles, again, the energy being involved, are not using anything to space the particles apart. So they're not being spaced apart. And so potential energy stays the same and no phase change happens. In segment D, we hit another plateau, so I'm going to highlight it like segment B. And so what's happening here is we are again at a blend. When you are boiling water, for example, it's not all gas, it's not all liquid, it's a mix. So here we have a liquid gas mix. And temperature, it's a slope of 0. There's no change. So no change in temperature means no change in kinetic energy. What we're doing, looking at the particles, is we're increasing the spacing, how much attraction is between one particle to the next. They're getting further apart, so potential energy has to be increasing, and that phase change then is vaporization. Okay. And then they continue to heat this further on, and we get this last segment in which the material is fully in the gaseous state. We see that the slope is back to being a positive, meaning an increase here. So kinetic energy is also going up. So all of that energy from the heat is being used to increase temperature. Again, potential and kinetic cannot change simultaneously. So then these 4 questions using the graph. So is this endothermic or exothermic? Well, obviously the temperature went from minus 40 to 130. So an overall positive slope. So that means energy had to be absorbed. And endo means absorb. So what phase is found at 80 degrees? Well, we have a big chunk here, 0 to 100. We can know for sure that that's somewhere between there. 80 probably falls closer here, and that's definitely in the liquid state. Boiling point. So you have to understand what is boiling. It's a type of vaporization. Boiling means that you're changing a liquid and it's changing to a gas. So where does that happen? That happens here in segment D, and that happens at approximately 100 degrees Celsius. So when it asks for a point, it's asking for a temperature. Melting point. Melting means for a solid to change to a liquid. So when we look at that, that's here in segment B, and that happens at 0 degrees Celsius. Okay, so the last thing we're going to look at is kind of a similar graph, but it has its own quirks of a cooling curve, and interpret that as well real quick. So here we have a cooling curve. We see that again, like I mentioned, the y-axis is always temperature. In this case, they're showing the x-axis in quantities of time that this material is cooled for 35 minutes. So again, we have segment AB here to start out. So I'm going to go ahead and highlight that. Segment AB, if you think about it, we have 2 plateaus, meaning 2 phase changes, and 3 slopes for our 3 states of matter. That tells us that here at the highest temperature possible, this has to be in the gaseous phase. So temperature is decreasing from 200 to 150, the delta T. So that's a drop. So that means the particles are moving slower, so kinetic energy is dropping. Again, we are removing heat because the temperature is going down. Heat can do one of 2 things. Heat can either cause a change in kinetic energy or a change in potential energy. Kinetic energy is changing here, so potential energy is not doing anything. We're not storing any form of energy. So from segment BC, this is a little bit weird to think about. So as we continue to cool this material, we're now going to change it into that hybrid of gas and liquid. Our slope is 0, so temperature is staying the same, so no change in the kinetic energy. A lot of people think, okay, well, this means an increase in potential energy, and that's not the case. Think about the arrangement. As we go from a gas to a liquid, are the particles getting closer together or further apart? They should be getting closer together. In order for those particles to move closer together, they need to have less stored energy. So what happens here is potential energy decreases. So again, as we remove heat, we're removing energy. So we can remove kinetic and we can remove stored energy. So the phase change happening here is condensation. All right. So we move back into another phase because we're back at a slope. So we look at segment CD. At segment CD, we're now fully in the liquid phase. Negative slope, temperature is going down. Change in temperature in the negative direction means that we are slowing the particles down, so less motion. That means no change in stored energy. We get to our second and only other plateau, DE. That is our second phase change where we have a mix. We're a mix of liquid and the solid state. The slope is 0, so no change in temperature, no change in stored motion energy. The stored energy is getting released from the system because, again, the particles are going to continue to move closer together as they work on going from the liquid phase to the solid phase. And that is called freezing. Okay. The last segment here is EF, where we lastly cool in that last segment. So here we're 100% solid at this point. Temperature continues to drop, so kinetic energy continues to drop, and no change in the potential. Here, is it endothermic or exothermic? Your overall temperature change from initial to final is a negative downward slope, so that has to be exothermic. What phase is found at 175? Well, we know that that's halfway between here and here, is approximately 175. Follow that over. That should be in the solid state. What is the condensing point? So again, we're looking for a temperature. Condensing point is a gas changing to a liquid. So that happened during segment BC, and that happened at 150 degrees Celsius. What is the freezing point? Well, freezing is a solid changing to a liquid. When that happens, that's segment DE, and that happens at 100 degrees Celsius. So quite obviously, this material is not water, it's something else. So that is how you interpret a heating and cooling curve.